Hello everyone. So today is the fourth and the last session of our chapter, which is entitled as Chemistry of D and F block elements. So today we will mainly discuss or focus our discussion on the inner transition elements, which are the F block elements. Now, with this discussion of this chapter of F block elements, we will draw the conclusion of this chapter, and we shall move forward to the next session that will be regarding the chemistry of coordination compounds, basically, where different kind of coordination chemistry we will be able to learn. So let's talk about today's session, which is mainly focused on the inner transition elements, that is the F block elements. So firstly, before going to any discussion regarding the F block elements, that I have devised some questions for you for ease in understanding. So firstly, I would like to have a brief idea or give you guys a brief idea about the position of the inner transition elements or the F block elements. Now, we shall start from the periodic table. So let's say this is the periodic table of where the elements are placed. Now, in the left hand side, we have these S block elements. In the extreme right hand side, we have the P block elements. In the middle portion, on the first side, we have this D block elements, and in the lower part of this D block, we have this F block elements or the inner transition elements. So this is the division of the periodic table. So if this is the hypothetical periodic table, so on the left hand side, we have these alkali metals or the alkaline earth metals, which are S block elements. On the right hand side, we have these P block elements. In the middle portion, on the upper half, we have these D block elements or the transition elements. And in the lower half of this section, we have these F block elements. So these F block elements are again divided into two classes of elements. First one is the lanthanides. So lanthanides are the elements which are following lanthanum. So this is lanthanum, and following this, the elements are called lanthanides. And again, in the lower section, just one group higher, we have this element actinium, and the elements are called as actinoids. So we have these elements lanthanides, which are following lanthanum, and again we have these elements actinoids, which are following lanthanum. So lanthanoids are the elements which are following lanthanum, and actinoids are the elements which are following actinium. Now, whenever we will discuss about lanthanides, we shall also include lanthanum in this discussion also, because lanthanum has a very high resemblance with the lanthanide elements. And this actinium also has very strong coordination, or you can say very strong similarity or resemblance with the actinoids. So whenever we shall discuss about lanthanoids, the topic of lanthanum comes into picture, or whenever we will talk about actinoids, the chemistry of actinium also comes into picture. So there are such 14 elements which are called as lanthanides following lanthanum, and similarly there are 14 elements in this actinide series also which are following actinium. Now all these lanthanides or actinides, or this you can say the F block or the inner transition elements, have one stable oxidation state. In case of lanthanides, it is +3. So this is one of the major similarities between the lanthanides, which is the very common stable oxidation state, that is +3. And now if we can discuss about their chemistry, it provides an excellent opportunity to examine the effect of very small or minute change in the size, or you can say the radius or the nuclear charge or the ionic potential along a series or along a period. So in this case, in case of lanthanides, the chemistry of actinides on the other hand is much more complicated actually. So in case of lanthanides, the chemistry is much simpler, but in case of actinides, the chemistry is a bit difficult to understand. Now, how this difficulty or the complexation arrives actually. Now, in case of actinides, what happens? There are a wide range of oxidation state that is available for actinides. Suppose there is an oxidation state of plus X. Now, X can vary from 0 to 5 in case of actinides. And also, in this case, the actinide series is actually radioactive in nature. So radioactivity also generates severe problem in studying these special kind of elements. That's why in case of actinoids, their chemistry, or you can say their study, becomes a bit complicated or difficult. On the other hand, in case of lanthanides, the chemistry is quite easier to comprehend. And in this chapter or in this session, we shall separately discuss about the lanthanides and also in case of the actinides. So this is the brief introduction of the elements of the inner transition elements actually. Now we shall move towards the next section, where we will basically know how we can actually assign the different ionic state or the atomic or the ionic radii of different lanthanides or actinides. Now, in general, the electronic configuration of all the length of the F block elements actually consist of this common term as 6s2. So 6s2 electronic configuration is common among the elements. Now, different 4f level occupancies are actually noted in case of lanthanides. So depending upon the electronic fulfillment in the 4f level, we shall have this variable kind of occupancy. So this variable occupancy actually results in the formation of different kinds of elements. Now, this is the electronic configuration of a free lanthanide atom. But whenever we will talk about this tripositive ion, that is Ln3+. So Ln is actually used to denote all the lanthanides in a nutshell. So Ln3+ is the tripositive ion, that is the most stable oxidation state of all the lanthanides that I have discussed recently. That is the tripositive +3 oxidation state is the most stable state of all the lanthanides. Now, depending upon the atomic number, this N will be different. That is 4Fn. Now, N is actually varying from 1 to 14. So that will be the electronic configuration of an Ln3+ tripositive ion. So we shall start with the first question, which is the why the separation among zirconium and hafnium is very much difficult from one another. So this is one of the major consequences for the separation. So zirconium and hafnium, these two elements are very much difficult to separate. Their chemistry is actually very much similar. So this is one of the major consequences of nothing but lanthanide contraction. So what is now this lanthanide contraction? So basically, when we discussed about these transition elements, that is the D block elements, we read about this lanthanide contraction previously. So basically, we will remember the same and how this can actually be correlated with the difficulty in separation of zirconium and hafnium. So basically, if we can write or can draw the periodic table over here, then only we can understand how this thing actually works. Now we have these D block elements, first of all here. So which starts with scandium, then we have titanium, then we have vanadium, and then we have chromium. Below scandium, we have yttrium. Below titanium, we have zirconium. Below vanadium, we have niobium. And below chromium, we have molybdenum. Now, below yttrium, there are two elements. First one is the lutetium. And here below zirconium, we have hafnium. So zirconium or hafnium are actually one below one another. And here in down to lutetium, we have this element lawrencium. And below hafnium, we have the element rutherfordium. Below niobium, we have this tantalum. And below molybdenum, we have this tungsten. Now, this is the basic position of the elements that we will discuss in this question about this lanthanide contraction. Now we have all these elements specified. Now our concern is regarding this position, which is zirconium and hafnium. So this is basically, both of these are basically D block elements or the transition elements. So why, when discussing about F block elements, why would we discuss about D block elements? So this is the beauty of the D and F block elements. So one elemental consequence will be actually delivered into another state. So here in this section, after lutetium, there occurs the lanthanides, which starts from lanthanum and goes till YB, is ytterbium. And from after lawrencium, so I shall denote this lutetium group as this cross, which is actually a lanthanide group, and the lawrencium group as right. And in the lower section, from lawrencium, we shall start and we shall end to NO. So from lanthanum, we shall have an end to lutetium, and from lawrencium, from this, we shall start with this section. After rutherfordium, we have this LR and we have this LU. And after this, from this element, when we shall start from the very element and we shall draw up to NO. So first series is nothing but these lanthanides, and the second series is actually actinides. So they are basically lying here. Since they are very much well in number, there are 14 and 14, 28 elements, and there were not enough space in the periodic table to accommodate. And since all these elements have very close similarity in reactivity with one another, that's why they were actually merged together and were placed below, in the below section or in the beneath section of the periodic table. So here we have 14 elements. Here also we have 14 elements. So these elements were actually coupled, or you can say merged, and kept in the below section of the periodic table. So they are popularly known as the lanthanides and the actinides. But how they are actually affecting the chemistry of zirconium and hafnium, that is the major question. So here you can see, from zirconium to hafnium, the principal quantum number is increasing. And as we know, in a group from top to bottom, the principal quantum number n actually increases, so the size of the metal also increases. Now the radius or the size actually plays a crucial role in the chemistry of the element. But what happens in this case, from zirconium to hafnium, the size doesn't increase at all. It remains very much similar. So here you can see the atomic radii of zirconium is 160 picometer, which is just as equal with that of the hafnium, which is 159 picometer. So you can see the striking resemblance in the almost identical radii of these two atoms. But why does it happen? So the lanthanides that are lying here, that actually plays the crucial role. The chemistry, the lanthanide contraction that I have written here. So what is this? So in case of lanthanides, you can see their coordination number. In the previous discussion, I have told that their electronic configuration is 4Fn. Now n can vary from 1 to 14. Now when the principal quantum number from left to right actually increases, the F electrons are actually filled. Now these F electrons have very poor shielding power. You know, the shielding power is actually in the order S greater than P greater than D greater than F. So this is the order of shielding of different orbital electrons. Now S orbitals have very poor, so at least the least effective shielding ability among. Now here you can see from left to right, in this case, the atomic number actually increases. That is the nuclear charge. So this is the nuclear charge. Nuclear charge actually increases from left to right, and also the electrons are filled in the 4f orbitals. Now with the subsequent filling of the 4f orbitals, since they are actually very poor shielder, they cannot shield the other electrons from the effectively growing nuclear charge. So the nuclear charge increases, and that actually pulls the valence electrons more tightly in the shell. That's why the size actually decreases with increase in the nuclear charge. So from left to right, the size actually decreases, though the nuclear charge increases, the atomic number increases. Now this cumulative effect of the contraction of the lanthanide series causes radii of the members of the third transition series to be very similar to those of the corresponding members of the second series. So this hafnium is actually in the third series and zirconium is in the second series. Now from this lanthanum to lutetium, the size actually decreases. That's why this zirconium to hafnium decrement is actually nullified by the decrement in the lanthanum to lutetium decrement because of the lanthanide series. And that's why we find very almost identical radii of zirconium and hafnium. Zirconium, it is 160 picometer, and hafnium has radii 159 picometer. So almost they are identical in nature. So that's why this is the reason why they occur together in nature. Zirconium and hafnium, they occur together in nature, and their separation is actually very, very difficult because they have similar chemical properties, because their size have become now identical. Though zirconium falls in the second transition series and hafnium falls in the third transition series. Now the next question arises, why are EU3 and YB2, europium and ytterbium, both of these two are very strong reducing agents? Now this is the chemistry of the oxidation state of the lanthanides. Now in case of lanthanides, the most common oxidation state is +3. In case of lanthanum, +2 oxidation state is found. In case of the other lanthanides, +3 oxidation states are found. Now occasionally these +2 and +4 ions can be found either in solution or in solid states. Now this irregularity of the oxidation state, firstly because of the ionization enthalpy. So as the ionization enthalpy changes, there occurs some irregularity in the oxidation state. So that actually arises mainly from the extra stability of the empty or half-filled or full-filled F subshell. That is 4F subshell. So in case of F, we have these 7 orbitals. So F0 is empty, F7 is half-filled, and F14 is the full-filled electronic configuration of these lanthanides. So depending upon the empty or the half-filled or the filled subshell of F, there occurs ambiguities or irregularities in the ionization enthalpies, and that's why the oxidation state can be different in these different shells. So firstly, we shall talk about in this question regarding EU and YB. So EU is europium. So europium has this atomic number 63. Europium has this atomic number 63. And the electronic configuration of the europium atom in the atomic state is 4f7 6s2. So this is the oxidation state, the atomic state of europium and its electronic configuration. So when we will talk about europium-2, the electronic configuration will be the field subshell, that is the 4f7. Now we shall come to the case of YB. So YB is nothing but ytterbium. So ytterbium has this atomic number of 70, which have this electronic configuration 4f14 6s2. So naturally, in case of ytterbium-2, the electronic configuration will be 4f14. So we have these two sets. First one is the europium-2, which is having a 4f7, that is the half-filled electronic configuration, that is stable. And second one is the ytterbium-2, which is having the full-filled F subshell, that is 4f14. So basically now you can argue that since both of these compounds are actually very much stable, that is the 4f7 and 4f14. So you should be able, so your approach should be europium-1 should be the major strong oxy-reducing agent. So europium-1 would have this 4f8 electronic configuration. So basically, if it loses one electron, it will go to the 4f7. So that is the very stable electronic configuration of 4f7 this wants to attend. So europium-1 should be the stronger reducing agent. So likewise, in case of ytterbium also, your approach should be ytterbium-1 should be the stable reducing agent, because both of them, if they loses one electron, they will be going to the either the 4f7, that is the half filled subshell, or the 4f14, that is the full filled subshell. But that is not the case over here. You see, though this 4f7 and 4f14 electronic configurations are very much stable, but stability does not always arise from the fact depending upon the electronic configuration. So the electronic configuration is obviously one of the major points or the parameters to determine the stability of a system. But besides that, there are other parameters also. So if we can consider only the electronic configuration factor over here, then europium-2 and YB2, why they are strong reducing agents, we cannot answer. Because both europium-2 and ytterbium-2 have very strong, very stable electronic configuration, that is 4f7 and 4f14. Now, in case of lanthanides, different things come into picture. So their chemistry is not as much useful, or you can say not as much prominent like the transition elements, that is the D block elements. So I have basically told you in the beginning of this class that in case of lanthanides, the +3 oxidation state is very much common. So the +3 oxidation state is the most stable oxidation state. So basically this has been calculated over the years by different experimental scientists, and they have come to the conclusion that +3 for different lanthanides is the most stable oxidation state. So that's why both of this europium-2 and ytterbium-2 have a strong tendency to reach out to the +3 oxidation state. So that's why they want to lose their electrons. So since they are actually very much prone to lose their electrons and go to the +3 oxidation state, that's why they are both acting as very strong reducing agents. So basically, if we, so here I have actually written in a nutshell, all the lanthanides preferably show their common class 3 oxidation states. Hence, despite having very stable F7 and F14 configurations, that is the half filled and the full filled configurations, respectively, europium 2 plus and ytterbium 2 plus have tendencies to attain their stable class 3 oxidation state. And if they want to attain the plus 3 oxidation state, they have to lose one electron. So that's why they are behaving, or they should behave as reducing agents. So this is the reason why ytterbium 2 and europium 2, both of them are strong reductants. Now these questions are basically very much informative in nature, and that's why I have clubbed all this together. So first one is the name some diamagnetic lanthanide ions. Diamagnetic lanthanide ions. So whenever we will talk about this diamagnetism, we shall have to understand in case of the F electrons, whenever the fulfillment, so in case of lanthanides, the major fulfilling of electrons is in the range that is F1 to 14. So F1 to 14, or specifically we can say 4F1 to 14. So 4F1 to 14 is the fulfillment of the lanthanide ions. So in this case, they are all paramagnetic, and most of the lanthanide ions, for your information, is paramagnetic in nature. But there are several cases where this diamagnetism arises. So we shall discuss about those. First one is the lanthanum. So lanthanum has this electronic configuration which is having 5d1, 6s2. So this lanthanum 3 is basically 4f0. So here you can see lanthanum has this configuration 5d1, 6s2. But whenever we are talking about lanthanum 3 plus, the electronic configuration will be 4f0 because all the 3 electrons will be lost. Now we shall come to cerium. So cerium is just the next one in the group. So after lanthanum, we have this cerium. So cerium is having electronic configuration. So from cerium, the 4f electron actually starts fulfilling. So we have this 4f1, 5d1, 6s2. So whenever we will talk about this diamagnetism, so we shall have to remove all the 4 electrons from cerium to make it diamagnetic. So 2 plus 1 plus 1, 4 electrons will be lost in case of cerium 4, and that's why it is the having the same electronic configuration as 4f0. Now there is an interesting case in case of cerium 4. So you saw in case of europium 2 and ytterbium 2, both of them are very strong reducing agents because they want to attain the class 3 oxidation state. Now you can see here in case of cerium plus 4, it also wants to attain the plus 3 oxidation state because it is nothing but a lanthanide, and we know the lanthanides always wants to attain their plus 3 oxidation state. So in case of cerium, so it will be very much prone to take up one electron and behave as a very strong oxidant. So since we are having this plus 3, so whenever the compounds will be in a plus 2 case, they would like to come to plus 3. So they will be very strong reducing agents in case of lanthanides. And whenever we are having this compound as plus 4, and this plus 4 also wants to come down to plus 3 by taking up one electron, so that will be an oxidant. That's why cerium 4 is a very strong oxidizing agent, but europium 2 or ytterbium 2, these two are very strong reducing agents. So basically, this is one of the tricks for you guys to understand how you can answer why something is a very strong oxidant or why something is a very strong reductant. So basically, we have 2 other cases also. So whenever we will talk about this, so F0 are actually the diamagnetism. So you can see F0 is nothing but the position of diamagnetic character. So what are the other possibilities where we can have this diamagnetic ions? So F14 is the other option to get the diamagnetic ions. So F14, so if we have to get F14, we have to start from the latter half in the lanthanide series. So first one is the ytterbium-2. So just in the last question we have discussed that ytterbium-2, ytterbium has this electronic configuration 4f14 6s2. So ytterbium-2 plus is 4f14. So we have ytterbium here. So ytterbium-2 is 4f14. Also after ytterbium, we have the last lanthanide atom as lutetium. So when we will talk about lutetium, lutetium has this electronic configuration 4f14 5d1 6s2. So lutetium-3 will have all the 3 electrons from D and S eliminated. So lutetium-3 will also be 4f14. So both of these 4f14 and this 4f0 all are actually diamagnetic in nature because all the electrons are paired up and they do not possess any unpaired electron. So in case of, we can see we have got 4 such cases. First one is a lanthanum-3, cerium-4, ytterbium-2 and lutetium-3. These 4 ions are diamagnetic in nature. So let's move forward to the next question. So next question is typically the question of the actinides, or you can say the next question is strictly informative in nature. So here the question is, what are the electronic configurations of americium, which is abbreviated as AM, and curium, which is abbreviated as CU, so CM. So first one is the americium. So americium is lying in the middle series of the actinide. So in case of americium, you see the electronic configuration is a noble gas, that is radon, which is followed by 5f7 6s2. So here in this case, we shall have to have this electronic configuration 5f7 7s2. And in case of curium, the electronic configuration is radon, that is an electronic, that is a noble gas, followed by 5f7 6d1 7s2. 5f7 followed by 6d1 7s2. In case of lanthanides, the electronic configuration would have been just one below than that of the actinides. So in case of actinides, it is 5f 6d 7s. In case of actinides, it will be 4f, that is in case of actinides actually. So I will abbreviate as AC and this one as LA. So in case lanthanide, it will be 4f 5d 6s. So one lower, one less than that of the actinide. So how we will remember? So actinide is one more than lanthanide. So that's how you will remember. So basically, this is one of the tricks to remember of the orbitals of the actinides and that of the lanthanides. Actinide goes as 5f 6d7s, and we shall actually subtract 1 from all of this. Lanthanum goes as 4f 5d 6s. So these two are the electronic configurations. Basically, this 6 will be, it is actually 7 that are mistakenly drawn. So this is actually americium, radon followed by 5f7 7s2, because the d electrons will be not fulfilled in case of americium. In case of americium, the F7 configuration is very much stable. And in case of curium, the electronic configuration will be radon followed by 5f7 6d1 7s2. So americium has this atomic number 95, and curium is just one above in the atomic number than that of americium, which is having the atomic number as 96. So the next question is, why is there a gradual decrease in size of the actinides across the series. Now, just as the lanthanide contraction, in case of actinides also, the contraction takes place. So this is basically the consequence of actinide contraction, just as the similarity in lanthanide contraction. However, the extent of actinoid contraction is far greater from element to element in this series because of the very poor shielding by the 5f electrons. So as the principal quantum number n actually increases from 4 to 5, the distance from the nuclear charge, the nucleus, also increases. That's why they are actually acting as very poor shielding. So 5f electrons have very much less shielding power than the 4f electrons. So in case of shielding, 5f electrons are far less than 4f. So that's why the very much poor shielding that is provided by the 5f electron is the reason why in case of actinoid contraction, which is just similar to lanthanide contraction, the extent is far greater. The next question is, which member of lanthanide series is well known to exhibit +4 oxidation state? So just in the previous section, I have told you about this question or this concept. First one is this is cerium. Cerium has this atomic number 58, and cerium +4 is one of the very strong oxidizing agent. So cerium +4 is actually employed as a very strong oxidizing agent. And how this cerium +4 can act as an oxidizing agent is quite interesting. So in case of cerium, the compound that is actually relevant in this case is ceric ammonium nitrate, which is popularly abbreviated as CAN. So CAN is the oxidant, which is actually a orange-red kind of crystal, which is very much used in the organic synthesis. Basically, its formula is ceric ammonium nitrate. So here we have two ammonium cations, which is NH4 followed by ceric nitrate. So Ce is the case, and we have 6 nitrate atoms. Here in this case, you can see there are 2 NH4 plus. So basically the charge of this anion is -2. And if we can take up the oxidation state of cerium as X, then X we have here, and we have 6 nitrates. Nitrates are mononegative ions, so 6 nitrates will provide total -6 charge, and totally it will be counting to -2. So X is nothing but 4. So this is a cerium +4 compound, and this one is the very strong oxidizing agent, because you know all the lanthanides have a tendency to come or arrive at their general and the most stable oxidation state, that is +3. Now this CAN is actually a orange red colored water soluble salt because it had so much NO3- groups attached to the cerium +4 standard, and it is a very standard oxidant that is used in the quantitative analysis of organic compounds. Now its popular name is ceric ammonium nitrate, but its IUPAC name is diammonium ceric +4 nitrate. It is water soluble and is actually crystallizable. It actually is as an orange red crystal, very much soluble in water. Now how it actually is prepared and how the core is actually fulfilled. So all the nitrates actually form a bidentate packing with the cerium center. So here you can see the cerium +4 center is here in the center, and we have 6 nitrate atoms where the donating group is oxygen. So here you can see 2 oxygen atoms each are donated from a nitrate group. So here you can see in the middle portion of each of these case, we have these nitrogen atoms, and this oxygen will be bonded to the cerium center. So from 6 nitrate atoms, we will be totally getting 12 oxygen atoms. So the coordination number of the cerium center is 12 in case of steric ammonium nitrate. Now, all the case in this case is chelate binding through a bidentate fashion. The ammonium ions are actually not involved in any kind of oxidation because it is just the counter cation of the entire system. Now, this steric ammonium nitrate, this anion CeNO3 whole 6 2 minus has TH molecular geometry, or you can say the idealized octahedral molecular geometry. Cerium plus 4 is a very strong oxidizing agent that I have already discussed. Against standard hydrogen electrode, is E0 value lies in the range 1.61 volt. It is an 1 electron oxidant. Now, it is even stronger oxidizing agent, you will be surprised to know, than this fluorine, which is having the E0 value as 1.36 volt. So in terms of oxidation power, cerium plus 4 is even stronger than fluorine or Cl2. Now, in the redox reaction, when cerium 4 will be converted to cerium 3, a 1 electron change is signaled by the fading of the color of the solution. You see this compound color is orange red, I have already told. And when it will be oxidized and it will go down to cerium plus 3, the color will be faded out to pale yellow. So this 1 electron oxidation of action of the steric ammonium nitrate is actually detected by the instant orange red to pale yellow, provided that the substrate and the product are not strongly colored. If the substrate or the product is also colored, then we will not be able to detect any change in the color from this orange red to yellow. Now, how this compound is actually prepared? Now, this anion, that is the steric nitrate, you can see the steric nitrate, CeNO3 whole 6 2 minus, is actually generated when we dissolve this cerium 2O3, cerium oxide, in hot and concentrated nitric acid. So this nitric acid actually oxidizes this cerium 2,3 center to cerium 4, and we get this anion, which is CeNO3 whole 6 2 minus, which is the core of the steric ammonium nitrate center. Now, this CAN or steric ammonium nitrate has a very much crucial role in the organic synthesis. It can be used to oxidize several functional groups, for example, alcohols, ethers, phenols, even some CH bonds also can be oxidized by the action of steric ammonium nitrate. Steric ammonium nitrate also provides an alternative to a very popular NEF reaction that is not actually can be discussed in the present scenario. But in case of heterocycles, the heterocycle can be generated by steric ammonium nitrate, or as a deprotection agent also, Ce+4 or the steric ammonium nitrate can be used. So we shall move to the next question. It is which is the last element in the series of the actinides? Write its electronic configuration. So the last element in case of the actinides is lawrencium, which is having the electronic atomic symbol as Lr. And its electronic configuration, I have already told, in case of actinides, it will be 5F, 6D, 7S. So in this case, it will be radon followed by 5F14. So all the electrons are fulfilled. The F subshell is fulfilled in case of actinides. 5F14, 6D1, 7S2. So we shall move towards the next question. Which kind of compounds are formed when lanthanoid metals are heated with carbon? So whenever lanthanoid metals are heated with carbon, we have these different kinds of carbides. So different kind of carbides can be formed. there are typically three different kinds of carbides that are produced whenever we take up this lanthanum and heat it with this carbon. So these are the products. First one is the Ln3C, second one is the Ln2C3, and the last one is the LnC2. So these three are the typical kinds of carbides that are formed when lanthanide metals are heated with carbon. The next question is, what happens when lanthanides are heated with sulfur and water separately? So when these lanthanides are heated with sulfur, it forms the sulfide. So Ln2S3 is formed, where the oxidation state of lanthanide is the most stable one, that is the +3. And whenever these lanthanides are treated with water, so lanthanide hydroxides are formed along with liberation of water also. So this is the typical reaction when you can actually produce the amphoteric basic or alkaline kinds of lanthanide hydroxides. The last question is typically a informative one, which is write some uses of lanthanide. So lanthanide elements also actually have uses in rather than these typical cases of organic synthesis or using as an oxidizing agent also. So firstly is the mixed metal. So mixed metal is an alloy which consists of a lanthanide metal, which is also the major one, which is 95%. So in mixed metal, the lanthanide is actually the major one, which is 95% consisting, which is coming from the mixed metal name is coming from the German name, which is mixed metal. It's an alloy of the rare earth elements, which is also having this D block element as iron, which is having only 5%, almost 90%, 5% of a lanthanide metal. And the other will be traces of the sulfur, a P block element, carbon, also a P block element, and two metals. One metal is a calcium, which is an S block element, and the other one is aluminium, which is a P block element. A typical composition actually includes, in case of the lanthanide metal, will be 55% almost will be cerium. And we have this 25% lanthanum. Also in some other case, to 15 to 18% will be neodymium. So this is also one of the different compositions of the mixed metal, when we have this 55% cerium, 25% lanthanum, and 15 to 80% of neodymium, and traces will be other metals. Total 80 plus 50, 95, and the less 5% will be the other metals. Now we also have the mixed oxides of lanthanides, which are employed as catalyst in the cracking of petroleum. And also some individual lanthanide oxides are also utilized as phosphors in the television screens and in some similar fluorescent surfaces. So these are the typical questions that I had to discuss with you in case of the inner transition elements or the lanthanides. So with this, we will draw the conclusion to this chapter of the chemistry of D and F block elements. And from the next class, we will be discussing on the chemistry of coordination compound.